Good morning, everybody. Today I'm going to go through Module 3 of this course, and that is basically Chapter 5 of the manual, is the chapter entitled Design of Paved Roads. The scope of this presentation is introduced here. There are 5 pavement design methods in the manual. I'll just mention them all briefly here, but we'll go through them in more detail later. The first one is called the AASHTO method. The second one is the Overseas Road Note 31 method. The third one is the Overseas Road Note 18 method, but that is only for upgrading and rehabilitation. The fourth one is called the TRL-SADC method, and finally the DCP-DN method. What I'm going to do is introduce these 5 methods to you. Then we're going to go through the key steps in the design process and guidance on the strengths and limitations of all the methods to help you choose which one to use. So the first thing we have to do when we're designing a new road is to make a decision. The decisions are what type of road to build. Do we want to build an earth road, a gravel road, or a sealed road? We're going to talk about the sealed roads in this particular lecture, but the decision has probably been made during the planning stage of the project. So let us assume that for now. So what decisions are we as the designer, structural designer, required to make? First of all, there'll be some preliminary information available to you. Measurements would have been taken of the traffic level, for example, and potential materials that we could use for construction and so on. So we'll assume that these decisions have been made and we're now sitting down at our desk to do the designs. The first decision we have to make is to determine or select the strength of the subgrade for the design process. Now, the key difference between the design methods that we're going to talk about is the fact that they don't always do this in the same way. So this is one of the major differences between the design methods. But, and this is quite important, most methods of design are flexible, provided the road authority allows them to be. In other words, whether the designer has some flexibility or not. So the methods do not constrain the designers, and in each method you have to decide how much risk you can take. So are you going to cater for the worst possible conditions or whatever? So the designer can make those decisions, and as I say, each method has its own way of dealing with this, and that is the important. So having looked at this subgrade strength for design, or how it should be assessed, the next decision you have to make is on the materials that you're going to build the pavement from. So there should be a lot of material tests available so you can see what materials are in your vicinity. You can also check whether you can relax the specifications for the low volume road. You do not need the major strength materials that you need for a high volume road. The first thing to do is to check that you can, whether there's some other materials available that are not so expensive. Now you've actually made almost all the decisions that you need to make. You've got your traffic level, you've got your subgrade strength, and you've selected the materials. You pick up your design catalogue, and basically the job's done, literally done. You won't believe that, but you'll see in a moment. Now we have some golden rules. The first and most important is that each method must be used in the way that the people who developed it, the authors of the method, intended. Unfortunately, this is not always made clear, with the consequence that methods can easily be used incorrectly. A good example, for example, is the one I put at the bottom of the slide. Method may ask you to base your design on the worst case moisture condition of the subgrade. This does not necessarily mean soaked, but many designers base subgrade strength on soaked conditions, whereas the worst case may be rather drier than soaked, and sometimes quite a lot drier. So if you base it on soaked when you shouldn't, you'll be over designing. That's perhaps one of the most common errors which we will come across later and show how to avoid. Golden rule 2, one way that this problem can be avoided is if the analysis of the source data that the authors have used to develop their design method is known and understood by the design engineer. But of course, it's quite unreasonable to expect the road designer to investigate the research on which the design methods have been based. So the onus is on the designers or the authors of the manuals to provide sufficient information to satisfy the road designer so that he himself is not taking any risks. Risk number one. Risk is a necessary but unwelcome aspect of civil engineering. It's addressed in different ways in the various pavement structural design methods, and this is what often causes uncertainty amongst the designers. For example, for large structures such as bridges, failure is very expensive, and so very safe designs are selected to withstand the very rarest severe storms. Andrew has mentioned storm intensity and storm severity. The storm that occurs on average once every 100 years is the most severe storm. Designing for the very rarest storm events, or maybe we should be designing our roads for something like that. But for small structures that are inexpensive to repair or replace, the 1 in 20 year storm, which is obviously not so severe, is used for design. So what do we do with our road itself, or more common storms? Well, we've already talked about the problem of climate resilience, and we're well aware now that the climates are changing. So the question of safety risk comes in even more now than it used to. Andrew's given you some advice on how to design structures and so on for severe storms and for climate resilience. But what do we do about the actual pavement itself? Few, if any, design methods actually define the risk levels that they are catering for. Road designers are well aware that over the design life of a typical road, there are many things that can go wrong. For example, there are likely to be severe storms. Ideal maintenance to keep the culverts and drainage ditches clear and to rectify erosion and surface damage cannot be guaranteed. So the designer cannot predict the future. He has to take a risk. And that, as I say, we'll come back to those risks when we go into the design methods in more detail. Thus, with no easy quantification of risk available, the designers often tempted to err on the side of safety. Perfectly natural human reaction. We don't know what the problems are going to be, so let's play safe. But to do so, the designers must understand how their design charts were devised and how they should be used. So that knowledge is important for actually doing your risk analysis. In the sections that follow here, the method of the way the design charts have been built up are described in order to help the designer understand and cater for the risk element. And we have later on, there is a summary of all the risk elements in each method to make it clear to the designer. So that's really an introduction to the guideline, and I'm now going to go briefly through the different pavement design methods. There's the list that I showed you initially. The first 5 are based on the California bearing ratio test, which most engineers will be familiar with, and that is for measuring the strength of materials, in particular the subgrade and the pavement layers. The last 2 methods are based on the use of the dynamic cone penetrometer. In method 7, it completely replaces the CBR test. CBRs are not used at all in that method. The method 6 incorporates both the DCP and the CBR method. So essentially, those are all the methods that we're going to talk about. The first method is the AASHTO method. It is based on a very famous road test which took place in the 1960s. A total of 332 trial sections of road flexible pavement were built in America, and these roads were trafficked for about 2 years. The traffic on the road test reached over 1 million vehicle axle loads on each test section. So you can see that it was a massive, massive test, and it led to development of a pavement design guide, which was first issued in 1961, but updated in 1972 and 1993. The 1993 version is still in widespread use in the United States and in many other countries, including some in Asia and Southeast Asia. But the reason that this particular method is included in the manual is it introduced some very important concepts that are used in many, if not most, all design methods today. So it's important to understand those concepts for all the methods. Key concepts that are used universally were introduced in the AASHTO method are the way that pavement damage is quantified, the concept of standard axles, which is to do with the amount of damage that an axle does to a road, the structural number, which is essentially the thickness of the structure that you're going to build. Very important, I've called it variability and reliability. What came out of the road test was that roads, even if they are built identically, can behave quite differently. There's a huge variability in performance, and the AASHTO road test, or at least the design method, was the first that really took that into account in the method itself. It's quite important, as you'll see later. And of course, the last thing here that was produced was an equation, if you like, the model of the design equation that is used to do the designs. So those are the 5 major concepts that came out of that road test. I have to go through them one at a time because, as I say, they are universal. Damage caused by an axle load of L tons is compared with the damage caused by a standard load of 8.16 tons. And the equation that relates to the damage is that the damage is proportional to the load raised to the 4th power, the so-called famous 4th power law. So any axle of any a load L is related to the damage caused by the 8.16 ton load, and we call that number the number of equivalent standard axles. And I think every design method that I've come across uses that. There are still 1 or 2 that still count vehicle numbers, but they're very few indeed. The most important thing, though, is that the total damage caused by all the axles throughout the design life of the road is then computed from the traffic data. The traffic data tells us what traffic is using the road now. It tells us what the future traffic should be. And the traffic is turned into equivalent standard axles and summed over the whole of the design life of the road. And that is the number that is used in the design methods. The second concept is the structural number. It is essentially the total thickness of the pavement, but each layer is weighted by its strength. So in the equation you can see before you, H is the thickness of the layer and A is its strength. And the strength is calculated from the normal methods that engineers use to measure the strength of materials. So that's all in the manual, and that's really quite easy to do. And by calculating the structural number of one pavement compared with another, you can immediately see which one will carry the most traffic. So structural number is the second concept. So the structural number of the pavement is thus the total thickness of the pavement made up of the different layers, but each one weighted by the strength of the material, with the strongest layer at the top, of course. The pavement thickness required, or in this case the structural number, actually depends on just 2 quantities, the traffic level and the strength of the subgrade. The CBR test is used to quantify the strength of the subgrade soil and also the strength of any unbound pavement layers in the proposed design. So at this point, we also have the design traffic and the subgrade strength. The structural number of the pavement required to protect the pavement from the estimated traffic loading is computed from the design equation. So we've basically essentially finished the structural design, because we have the structural number to protect the pavement. All we now have to do is convert the structural number to actual materials, and then the layer thicknesses can be computed. and you know how the structural number is calculated. I've explained that. So to convert that into the layer thickness is quite simple. Now we can do this for a whole range of subgrades and traffic levels using the design equation and produce a design chart. Now this is how most of the methods are presented to the designer. As you can see from the chart, the traffic level is along the top, and down the left-hand side is the subgrade class or the subgrade strength. And in each little box is a little diagram showing the various pavement layers that you need and their thicknesses. So, as I say, in this particular case, we've used the design method 20 times and produced 20 designs covering those ranges of subgrade strength and traffic level. And that is the easiest way that designs are presented, and most methods do it this way. So what's the problem? We've got the subgrade strength, we've got the traffic, we've got the structural number, and we have worked out the thicknesses. What is the problem? Well, the problem is the designer will say, which is the best method, which is the most reliable method, and which one should I use? And this is really the heart of the chapter and of the guide, to show you or to advise you on how to do this. First of all, golden rule number 3, the methods are empirical and based on successful designs. The golden rule is the method must be used within the range of conditions in which it was developed. There must be no extrapolation of any parameter. We mustn't go to different climates. We can't go from the desert to frozen conditions in the north of Nepal. We mustn't change the materials. We must stick within the traffic range for which the design method is being developed, and so on. This is really quite important and is a constraint on the use of certain methods in certain places. This is not a golden rule. I've called it rule number 4. It's not a golden rule, but it's a confusing and useful rule. Methods with a history of successful use are fairly reliable because they've been in constant use for many years and people are happy with them. But new research is showing that they may be a little conservative. In recent years, we've been showing in recent research that the pavement thickness designs are probably conservative because in the past, if a road did not perform very well, the reaction of the engineers or the highway agency is to make the next road a bit thicker. But it isn't necessary extra thickness that would have made the road perform well. It's not very often, or not as often as we used to think, that subgrade failure or failure to protect the subgrade is the main reason for failure. So in the past, I think designs have got conservative, and the new data is showing that some of the older methods that have been successful are slightly conservative, and we are revising those as we speak. How do I said before that the different methods use different methods of estimating the subgrade strength for design. Overseas Road Note 31 asks you to find the weakest anticipated subgrade strength, the weakest anticipated CBR over the design life of the road. There are various ways that can be done, and those are described in the Overseas Road Note 31 manual. Overseas Road Note 18 is for rehabilitation design or strengthening. So you're basically dealing with an existing road. So the subgrade strength is the strength of that existing road. The TRL-SADC method uses a different method of anticipating the subgrade strength. The method is based on the performance of existing roads in certain climates and certain drainage conditions. And as long as you are reproducing those conditions, then your design should last as well as the ones on which the method is based. It's slightly different, as you'll see later. The fourth method we've called the foundation method. That uses a soak CBR of the subgrade. That is not necessarily the worst condition, but it's the method on which the system was based. And the DCP-DN method, the subgrade strength for design is one of three possible values. It's either that the optimum moisture content for that particular material at the specified density is at 3/4 of the optimum moisture content, or if you're in a severe climatic area, you use the soaked value. So three different values. That actually turns out to be fairly similar to the Overseas Road Note 31 method, but that's by the by. What I've done now in the guide is give you a list of the comparison of the methods in terms of their strength and the limitations as to use. So we have a number of charts here that go through the strengths of each method and the limitations. AASHTO method was based on the AASHTO road test, which took place in one part of the United States on one climate and obviously one subgrade. So it is not considered initially to be a worldwide application, but the power of this particular method is that the way the analysis was done and the equation that was produced means it can very easily be adapted or calibrated to suit a wide range of conditions. And that is one of the reasons why it's used in so many countries now, and some countries, because of that powerful statement. It can be easily adapted or calibrated. Calibrated is perhaps the best word to use to suit a wide range of conditions. It is also the only method that includes a true, what I've called a reliability factor, that recognises the inherent variability in road performance. That is taken into account explicitly in the design equation and allows you to design essentially to cope with variability. You can design for, you can choose your level of risk, in other words. I did say earlier on that each method deals with risk in a different way. This method allows you to design for 95% reliability, very, very little risk of failure. I mean, of course, that means that you can also over-design. And for our low-volume roads, we would want to make use of different levels of reliability. Now, the other final strength is that because it's used so widely, there's a lot of people who have used it before. There's a lot of the documents in the literature, a lot of debate and feedback amongst practitioners. So that makes it a strength because you can look up a lot of things on the internet. Limitations, the one that's probably most serious from our point of view, it is not adequately tested on strong subgrades, but as I say, it can easily be calibrated to do so. It's primarily used for high volume roads, hence the manual is a thick, substantial, I call it a substantial document, but this should not deter users. As I said, it's been used successfully in the USA for 60 years and in many other countries. The Overseas Road Note 31 method is the method that TRL produced for specific use in tropical environments. The subgrade strength for design can be based on any moisture content. In other words, the worst condition, the long-term equilibrium condition, whatever the designer wishes to choose, and there's some guidance on doing that in the manual. It offers designs for 8 different road types, including stabilized road bases. So it's not just natural gravel, not just natural gravel road bases, which is generally what one would use for low volume roads, but occasionally it's necessary to stabilize a layer. It's been in use for about 40 years in a wide range of climates. The limitations of the Overseas Road Note 31 method, 3 traffic classes below 1 million standard axles, and we would like more, I think. For low volume road material specifications, the Overseas Road Note 31 specifications are a little conservative because, as I say, there are only 3 classes for the very low volume roads, and Overseas Road Note 31 goes up to about 30 million, so it covers the whole range. The TRL-SADC method is based on some research carried out by TRL in 3 countries in Africa. It offers 2 design charts that are based on the climate and the basic drainage quality. By drainage quality, we mean sealed shoulders, we mean the height of the crown of the road above the drain, etc., in the way that Andrew described it in the previous module. It provides 5 traffic classes up to 1 million standard axles, so it should be sufficient there to cover the range that is required for low volume roads. Subgrade strength is measured in the soaked state, but that doesn't mean that we're expecting the subgrade to be soaked in reality. We're just labeling or indexing the subgrades that are available. So basically, experiments on which the method is based, the subgrades were soaked, and if you have a soaked subgrade, your subgrade is soaked, has the same value, then it will behave in the same way that the experimental pavements behaved. And of course, those in the design chart are the ones that behave well. So there should be no worry about subgrade strength. The material specifications are comprehensive, but again, they've been tailored to a pragmatic level suitable to the task of a low volume road. In other words, they're not as conservative as the Overseas Road Note 31 material specifications. In fact, I suppose the best description of the TRL-SADC method is it's essentially very similar to Overseas Road Note 31 in form, but modified. The materials specifications are modified to capture the results of recent research. The main limitation, I think, is that it's the countries in which the method was developed are on an international scale would be classed as moderate in terms of climate. We don't have monsoons, but we have, certainly in some of the countries, we certainly have some very severe conditions these days. The third method is what we called the foundation method. And in this method, we construct a foundation which will be the same for all structures for a particular traffic level. In other words, we form a reliable foundation that can be readily and routinely checked by measurement of its bearing capacity by means of the normal simple tests for bearing capacity using a falling weight deflectometer, a lightweight deflectometer, or plate bearing test. As we know, the greatest variability in the structure of a pavement comes through the subgrade, because subgrade is very variable. On the brows of hills, the subgrade can be quite dry and strong, but in the valleys, where rivers are flowing, it can be wetter and weaker. And so as you go along any road, your subgrade is varying quite a lot, even though you've designed the road on the most uniform sections that you can define. So the variability in the structure comes from the subgrade. And so if you check your foundation before you put the rest of the pavement layers on, you can identify quickly where weak areas are, and they can be corrected before the main structural layers of the pavement are put on. And this is a good way to enhance quality and therefore performance. In principle, the same method can be adapted to other design methods, but it hasn't been done yet. The disadvantage or the limitations are that you really do need to have the equipment available for doing the checking, which, as I say, is the main advantage of the method. I suppose one of the other limitations is that, again, it's based on research in East Africa, which is not one of the most extreme climates. The Overseas Road 18 DCP CBR method is for upgrading or rehabilitating an existing road. And so one of the most important features is that we must get as much information as possible about the existing road. And to do that, the DCP is a very valuable instrument because each test takes a very short time, and therefore you can take many tests which will give you details about the existing thickness of the layers and the strength of the layers. And it also allows you to define uniform sections that can be treated separately fairly quickly. However, it's not just the strength testing of the existing road that's important. The most important thing for upgrading or rehabilitating an existing road is to do a study of what has caused the poor performance of the road to be what it is. It's a forensic study. It's not just the thickness and strength. It may be just a drainage problem. It may be whatever. You need to do the forensic study, and Overseas Road 18 is a manual that shows you how to do that. Next method is the DCP-DN method. This is based on the DCP test, which completely replaces the CBR test. The method was established in South Africa, is not yet established in more severe environments, but being trialled in several countries. The use of the DCP to identify uniform sections saves on the cost of test pits, but obviously some test pits are required. Less stringent material specifications, hence there's a flexibility to use different locally available materials, but this is also being revised. Less stringent materials specifications means that selection of materials could lead to an increased risk, and that's why more work needs to be done on this. It's also very applicable in situations with limited laboratory equipment, which is the case in many of the more remote parts of the country or remote parts. So that's a very useful strength. One of the limitations is that the method assumes that the subgrade is between 450 and 800 millimeters below the finished pavement surface. And this is not always the case, so that can create a little bit of a problem. The method is only applicable to natural and treated materials. It doesn't deal with strengthened or cemented materials. And the method is not applicable on roads that require deep cuts and fills of more than 1.5 meters, because clearly the DCP is a measurement system of limited depth. The handle, I think 1 meter is the normal, but there can be extensions up to about 1.5 meters, but obviously not applicable if you need more than that. So next method I've called purely empirical methods. These are methods that are not designed in any design sense. The method is specified in very precise rules of construction, which are not varied. So their advantages that they deal with very coarse materials like Telford bases and large macadams. These materials can be extracted or obtained from crusher plants. The methods are often labour-based and hence create employment. And they're often very climate resilient because the materials are not largely affected by the soaking or saturation with water. Quality control during construction is not a major challenge because the rules of constructing them are very, very, very precise. Limitations are that obviously many areas will not have an abundance of suitable rock, and by virtue of the fact that they are labour-based, they're often quite slow to construct. Finally, we come to concrete methods. Concrete roads have their place in low-volume road construction. They are very highly suited in areas where climate is a serious problem because they are not seriously affected by being soaked or saturated. They're quite well suited for steep gradients where other materials might not be suitable. Quality control is not particularly difficult. It doesn't create a challenge, and the final strength of a concrete road is that it actually has very low maintenance costs. The limitations are that it obviously is a high initial cost compared with other methods. Sometimes the fact that it requires sufficient caring if the design is to be achieved, it's not always possible in areas of water scarcity or where supervision is poor. So curing time is an important issue, but shouldn't be too difficult to cope with that. So there are limitations. So basically, we've been through some of the risks, we've been through the strengths and limitations of some of the methods, and hopefully I've given you a good idea of how to select the method that you want to use and which one to rely upon. So with that, I would like to say that is the end. Thank you for your attention.